Okay, so we're going to continue our discussion of some of the reactions that benzene and its derivatives can be involved in. In this video, we're specifically going to consider reduction reactions. So this is something that the book talked about early in the chapter, but I kind of skipped it. When it was talking about the stability of benzene, it was talking about hydrogenation reactions. Because the benzene is so stable, we can achieve hydrogenation with hydrogen gas and a catalyst. Like we've learned, we can hydrogenate other alkenes. The difference is we need pretty harsh conditions in order for this to happen. We need upwards of 100 atmospheres. So that's a really high pressure in order to force this hydrogenation. So one kind of cool thing, if we have the benzene ring and then other alkenes present, we can selectively hydrogenate just the other alkenes using less harsh conditions, right? So instead of doing 100 atmospheres, if we just do 2 atmospheres, we'll hydrogenate this alkene, but it's going to leave the much more stable benzene ring alone. So another way that we can reduce benzene is with a process called Birch reduction. It's named for an Australian scientist who studied a lot of the details of this reaction. And the reagents may look familiar. We used last semester to selectively reduce an alkyne, we used dissolving metal reduction, which gave us the trans alkene, and we used sodium in liquid ammonia. Well, if we use similar agents, sodium and liquid ammonia, in the presence of methanol, we'll get this Birch reduction. Now, if you notice, we didn't completely reduce the benzene ring, right? We only lost one of the multiple bonds, and we still have 2 double bonds. And in fact, the double bonds are directly opposite each other on the benzene ring, and then at opposite ends, we also now have 2 sp3 hybridized carbon atoms. So let's look at the mechanism for this Birch reduction. All right, so this mechanism looks kind of nasty at first, but it actually turns out that it's just repeating the same process more or less twice. So the first thing that we do is a single electron from the sodium is donated to the benzene ring. Then one of the electrons from the neighboring pi bond combines with that lone electron from the sodium to make a lone pair and a negative carb anion. The other electron from this pi bond combines with one of the electrons from an adjacent pi bond to form the double bond here, and then the one remaining electron that doesn't have a pair ends up being a radical opposite from the anion. Then the methanol is used for a proton transfer, so the negative ion steals a proton from the methanol, leaving us with a radical. Let me push this other part up. So this is the same radical that we made in this step. Now the sodium donates another electron, though in this case obviously much simpler. We just form a pair here and now a negative anion, and then we finish off with a similar step to what we had up here, where we have a proton transfer from another methanol molecule to give us our product. All right, so let's talk about the regiochemistry of this Birch reduction. So if we have an alkyl group attached to our benzene ring, this alkyl group acts as an electron donating group. And so it actually destabilizes the anion intermediate that we saw in the previous mechanism. And so what that means is any alkyl group that we have on the benzene ring, it doesn't want to be reduced. And so we're going to keep a double bond connected to that alkyl group. And so the carbons that end up not having the double bonds that become sp3 hybridized, they're ones that did not contain the alkyl group. So the alkyl group acts as an electron donating group. If instead we have an electron withdrawing group, like a ketone in this case, and the reason it's electron withdrawing is because if we imagine this resonance structure, now we have an allylic carbocation, and so this is going to remove electron density from the benzene ring as we distribute that positive charge throughout the benzene ring. All right, so you don't necessarily have to draw this to be able to answer the question about the regiochemistry. Just recognize that the carbonyl is an electron withdrawing group, that stabilizes the negative anion that we form as an intermediate, and so a carbon with an electron withdrawing group is now more likely to be reduced. And so we're not going to see the case where the carbon with the electron withdrawing group is not reduced. So an alkyl group is going to maintain the double bond. An electron withdrawing group is going to end up losing the double bond. So let's look at a couple examples. So we want to predict the major product of this reaction. So we have the sodium with liquid ammonia and the methanol. So this is a Birch reduction. And then we have two electron donating groups. These alkyl groups are going to act as electron donating groups. So they're not going to want to be reduced. So in our final product, we're going to need double bonds on opposite sides of the molecule. But if we can, we want each one of the alkyl groups to have to be part of a double bond. So I think the way we can do that we can just sort of do them one at a time, right? For this alkyl group, we need to put the double bond here, in which case the double bond has to be on the opposite side here, and then this alkyl group gets left off, right? If instead I put the double bond here, then putting one across the ring would put it here, and in that case, both alkyl groups are not going to be reduced. So I think that's the product that we're going to form. Okay, similar idea. Again, we have reagents that are going to lead to the Birch reduction, only now we have an electron donating group, an electron withdrawing group. So the alkyl group should maintain a double bond in the final product. The electron withdrawing group should be reduced, and so it should not have a double bond on this carbon in the product. So we can draw our skeleton. And so if I think about this carbon, I can put, right, this wants to have the double bond, so I can either put it here, in which case the other double bond across the ring would go here, and my electron donating group will not be reduced, so that's not ideal. Alternatively, right, the electron donating group should maintain the double bond, so I could also put the double bond here and here, and I think that's the way we want to go, because now my alkyl group was not reduced, but the carbon with the electron withdrawing group was reduced. And so this should be our product of this reaction.